So today we are starting lecture 6 of helicopter dynamics. We are going to discuss periodic motion and I am Dr. Ranjan Ganguly. Now this is an example of typical periodic motion with time period tau. So you can see here the graph of x of t versus t, and you can see this is a typical response for this system. Now what is interesting here is that after this time tau, the motion essentially repeats. So this is a characteristic of periodic motion, and this is important for rotor dynamics because the rotor system tends to be periodic in steady state or is periodic in steady state. Now the difference between periodic motion and typical simple harmonic motion is that frequencies of several frequencies will be there, or vibration of several frequencies are simultaneously present in periodic motion. So essentially periodic motion has several frequencies in its vibration, which we saw in the previous slide. Now typically when you excite a multi-degree of freedom system, vibrations at each frequency will contribute to the resulting motion, and so you will get a complicated periodic waveform. In contrast, the simple harmonic motion which we discussed in our previous lecture, there was only one frequency given by the circular frequency. Now because of the huge presence of periodic systems in rotor dynamics, it's important to spend some time looking at representation of periodic motion in Fourier series. Because one of the greatest inventions in periodic system was the fact that Fourier showed that a periodic motion can be represented by a series of sines and cosines, as you see here. So let us say xt is a periodic function, then we can write it out like this. So essentially you have one constant term driven by a0, and then you have a term involving cosine frequency into t plus cosine another frequency into t, and similarly you have sine frequency 1 into t, sine frequency 2 into t, and so on. So here these frequencies are 2 pi by tau, that's the starting frequency, and all the other frequencies are multiples of this particular frequency. So the important thing in Fourier series is how do we now find the coefficients of this Fourier series expansion. That is, we want to find a0, a1, a2, b1, b2, and so on. Now if you are familiar with trigonometry, you would realize that if you multiply both sides of this equation by the appropriate cosine or the sine terms and then integrate this expression on period tau and use various trigonometric simplifications, then some of these terms are going to vanish and you are going to get many of these coefficients. So let's try to do that. So these are some of the integrals which you can use. So here you see that whenever you have cos and sine in terms multiplied together, then these are 0 whether m is equal to n or m is not equal to n. But in these two cases, if you have cos and sine terms, then these are 0 when m is not n, and remaining cases when m is n, it is tau by 2, and the same situation here. So this means that a large number of those terms are going to vanish, and then you are going to get closed form expression for the different coefficients. So these are the expressions you are going to get for an and bn. The expressions are 2 by tau, the integral here, and then whatever function xt you have got, the periodic function, into this cosine term dt, and similarly bn is this xt into this sine term dt, and again the integral here. So these integrals can typically be found for many functions if you have explicit forms of those functions, and if not, you can numerically calculate them also. So that's something which can be found. Now, there are many situations and in many books where you will see that Fourier series are also expressed in an exponential form. And this comes from the fact that I can write cos in this form using these exponential here, and I can write sine in this form using these two exponentials here. Now, these two expressions can then be plugged back into the Fourier series and you get this particular expression here. You have a constant term and then you have the sine terms and the cosine terms, and then you combine all this together, you get this here, and you can rewrite this in this form here. So what it is telling you that x of t could be expanded in an exponential series using this form here. Now some books use this exponential series because it is more compact, but sometimes it is also somewhat difficult to understand because again you are bringing in complex numbers into the picture here. But that again is a choice of the person interested in the subject. So again it's essentially the same thing. You are expressing the periodic function in terms of sines and cosines, except that the sines and cosines are actually contained inside these complex exponential numbers. So again, the Fourier series coefficients C0 and Cn can be found out like this, and they are related to the A and B coefficients using these two equations. And here Z is given here and the Z star is given here. Now, in many cases, you can greatly reduce the computational effort required to perform these integrals if you realize that x of t is an even function or an odd function. So let's define these particular things. Now, typically you can write x of t as some even function and some odd function. So for example, if you have symmetric functions such as you substitute negative here, so et should be same as e minus t. So for example, in cos you can see this thing actually works. So cos of negative omega t is same as the cos of omega t. Same thing can be expressed in many more functions which are essentially of this nature. Now if you are looking for an odd function, the thing which is true is that ot is negative of o minus t, which you can clearly see with this sinusoid here. So again, depending on whether a function is of the cosine sort or the sine sort, many of those integrals will become very simple. So for example, you see that in any cases where a function of the type et is multiplied by this sinusoid, you get 0, and a function of the type ot is multiplied by this cosine function, you will get 0. So all these terms will essentially cancel out, resulting in a lot of simplification. Now there is also a possibility that you could plot the coefficients of the Fourier series with respect to the different frequencies, and in those cases you would get a series of discrete lines which are sometimes known as the Fourier spectrum, and sometimes people show the Fourier spectrum to refer to periodic systems. Generally in those graphs what is plotted are the absolute values, so you essentially get the root of an square plus bn square and you can plot it. You can also sometimes look at the phases given by this particular phi n. Now one of the issues in doing any kind of harmonic analysis calculation is that you will finally need to resort to a computer for most realistic problems. And one of the ways to increase the efficiency of this process is to use the fast Fourier transform, and that is often used to minimize computer time when you are calculating the Fourier transform. So I'll stop at this point on this lecture 6. We will proceed in the next lecture on spring mass systems.